All right, this will be part 4 of Calc D assignment 11. We are either finding a potential function or showing that this vector field is not conservative. So 14. The vector field is e to the x quantity z plus 1, comma, negative cosine y, comma, e to the x. If this is in fact conservative, then that will be partial x, partial y, and partial z. So what I'm going to do is start with partial x and just integrate with respect to x, which will give me my potential function is e to the x quantity z plus 1 plus an arbitrary function of y and z. I will now take the derivative of this with respect to z. It doesn't matter. You could do it with respect to y or z at this stage. I'm choosing to do it with respect to z because if I do it with respect to y, it's not really getting me anywhere. Well, I mean, it'll get me to the same place. Whatever. Choose your order. I'm going with respect to z. I get e to the x plus partial z of g. Compared to what we think partial z is, which we think is e to the x, which would mean that partial z of our arbitrary function should just be 0, which means our arbitrary function is not actually a function of y and z, definitively. It is just a function of y, and so I'm going to update what I think my potential function is. So now I have e to the x quantity z plus 1 plus h of y. Find the derivative of this, the partial derivative with respect to y, and I get that partial y should just be h prime of y. Compare this to what I think partial y is, which is negative cosine of y. Integrate this with respect to y, gives me negative sine of y, and update what I think the potential function is to get e to the x quantity z plus 1 minus sine of y. That is our potential function. All right, let's look at another one. So we are given the vector field 2xy plus 5, x minus 4z, negative 4y. If this is in fact conservative, then this will be partial x, partial y, partial z of our potential function. So let's start by integrating partial x with respect to x and see what we get. That's going to give us x squared y plus 5x plus our arbitrary function of y and z, which would have a derivative of 0 with respect to x. That's why we throw in that arbitrary function. So now we will find partial y of this thing. So partial y of this thing is going to be x squared plus partial y of g. Compared to what we think that partial y is. So that is given as x squared minus 4z. Subtract x squared from both sides, and we get that partial y is just negative 4z. We're going to integrate this with respect to y. That'll give us negative 4yz plus some new arbitrary function of just z, which would have a derivative of 0 with respect to y. So update what you think your potential function is. Replace g. X squared y plus 5x minus 4yz plus h of z. Find partial z of this thing. So partial z is going to be negative 4y plus h prime of z. Compared to what you think that partial z is, which was negative 4y, which tells us that h prime of z would be 0. Update your potential function, and we get x squared y plus 5x minus 4yz. That's our potential function. So this is a conservative vector field. We were able to find the potential function. All right, let's look at the next one. So we have our vector field is yz e to the xy, xz e to the xy minus z, e to the xy minus y. All right, so if this is conservative, it'll be partial x, partial y, partial z. I'm going to start by integrating partial y with respect to y. Again, it doesn't really matter where you start. I'm just choosing there because it looks like the best starting place to me. So I would think if I integrate this partial y with respect to y, I get z e to the xy minus yz plus our arbitrary function of x and z because we integrated with respect to y. All right, we'll find partial x of this thing. So partial x of this thing gives me yz e to the xy plus partial x, so there's no x's in yz, so that derivative is 0, plus partial x of xz. All right, compare to what we think partial x is, which is yz e to the xy. So that would mean, because they match up, that partial x of g is just 0, which means we can update what we think our potential function is. We no longer think that we have an arbitrary function of x and z. We now think we only have an arbitrary function of z. So I'm going to say that I think my potential function is z e to the xy minus yz plus h of z, the new arbitrary function. find partial z of this. So partial z of this thing is e to the xy minus y plus h prime of z, compared to what we think partial z is, which is e to the xy minus y, which tells us that partial z, or rather h prime of z, should be 0. So update what you think your potential function is. A potential function could be z e to the xy minus yz. So this is conservative. We found a potential function. All right, we got one more to do. Number 17, we're actually doing a line integral. Evaluate the line integral 2xyz dx plus x squared z dy plus x squared y dz. What I like to do, over the path r from 0 to 2, what I like to do is actually write out the vector field. I don't know if everyone likes to do this, so I'm going to write that f is 2xyz, comma, x squared z, comma, x squared y. So I just pull them off of the line integral that I'm given. So this I need to think of as partial x, partial y, partial z. I'm going to try to find a potential function, and then I will use the fundamental theorem on this. So I'm going to start with partial x, integrate that with respect to x, and it'll give me f of xyz is x squared yz. So I am thinking, I'm not even going to put an arbitrary function. I'm just going to find partial y and then partial z of this thing. If I find partial y of x squared yz, I get x squared z. So that works. If I find partial z of x squared yz, I get x squared y. That works. So this is a potential function. So I'm not going to go through the whole thing because this one, by inspection, you can pretty easily find your potential function. So now I need to just figure out where I'm starting, where I'm stopping, and use the fundamental theorem on this. So I'm trying to do this line integral of f dot dr, and that should be f of where we end minus f of where we start. So we end at r of 2, and don't forget we're taking that and we're going to plug it into our x squared yz. So that's where f of where we end minus where we start would be r of 0, which is, we're plugging into r, so we get 0 squared sine of 0 e to the 0, so 0, 0, 1. So what we're doing is f of 4, 1, 1, where we end, minus f of 0, 0, 1, where we started. This is the function we're plugging into, so that's going to be 4 squared times 1, and then, 0, 0, and 1, but that's just going to give us 0. And so overall, we are getting just 16 as our answer to this. And that's it. That's the entire problem set. I hope this was helpful, and good luck.